The year was 1940. High above the English Channel, Flight Lieutenant Geoffrey Wellham gripped his control stick with white knuckles as a German Messerschmitt Bf 109 filled his gun sight. At just 19 years old, he was about to discover why the Supermarine Spitfire possessed the most dangerous wing ever designed for aerial combat. The Messerschmitt pilot banked hard left, pulling his fighter into a vicious turning duel that would test the very limits of aerodynamic engineering. Wellham followed, feeling his Spitfire respond with an almost supernatural agility that defied the laws of physics. As both aircraft spiraled downward in a deadly dance, the young RAF pilot pushed his throttle forward and pulled back on the stick with crushing force. 4.5 times the force of gravity pressed him deep into his seat as his vision began to tunnel. But the Spitfire held together, its thin elliptical wing, just 13% thick at the root, tapering to 9.4% at the tip, carved through the air with mathematical precision. The wing that aviation experts would later call the most dangerous design in the world was keeping him alive. This was the weapon that would define the outcome of World War II in the skies over Europe. Yet its creation began not in wartime desperation, but in the pursuit of pure speed over the Mediterranean waters of the Schneider Trophy races. Lieutenant Reginald Joseph Mitchell understood the fragility of aircraft better than most designers of his era. Having learned his craft during World War I, he had witnessed firsthand how quickly aluminum and fabric could transform into twisted wreckage. This obsession with pilot safety would drive every decision he made, even when designing aircraft capable of speeds that pushed the boundaries of what seemed possible in 1934. Mitchell's path to creating the Spitfire began with failure. His Supermarine Type 224, built to Air Ministry specification F730, could barely achieve 230 miles per hour, 20 miles per hour slower than required. The aircraft's thick inverted gull wings and fixed landing gear created so much drag that it was outperformed by existing biplane fighters. Aviation journalists nicknamed it the Flying Dustbin. The humiliation stung deeply, but Mitchell had already begun work on something revolutionary. Drawing on his experience designing high-speed racing seaplanes that had dominated the Schneider Trophy competition from 1922 through 1931, he envisioned an entirely different approach to fighter design. His racing aircraft had taught him that speed came from managing airflow, not simply adding more power. Working alongside Canadian aerodynamicist Beverly Shenstone, Mitchell began exploring wing designs that could solve two seemingly impossible requirements. The new fighter needed thin wings to minimize drag, but those same wings had to be thick enough to house retractable landing gear, ammunition, and 8 Browning machine guns, more firepower than any fighter had ever carried. The solution emerged from pure mathematics. An elliptical wing planform created the most efficient possible distribution of lift across the wingspan, generating the lowest induced drag of any configuration. Frederick Lanchester had proven this theoretically in 1907, but no one had successfully built such a wing for a high-performance fighter. Shenstone later recalled Mitchell's practical approach to the challenge. "I don't give a damn whether it's elliptical or not, so long as it covers the guns." But the truth was far more sophisticated. The final wing design wasn't a simple ellipse at all. It was actually 2 semi-ellipses joined at a common axis, creating a planform that was both aerodynamically optimal and structurally sound. The wing's leading edge followed one elliptical curve, while the trailing edge followed another, larger ellipse. This double ellipse configuration allowed the main structural spar to run straight across the wing at a right angle to the fuselage center line, exactly along the quarter chord line where the center of pressure would naturally fall. This alignment prevented the wings from twisting under load, a phenomenon that could prove catastrophic during high-speed combat maneuvers. On December 5, 1934, Mitchell's team finalized the Type 300 design. The prototype, registered K5054, began construction immediately, even as the designer battled the cancer that would eventually claim his life. So, when test pilot Captain Joseph Mutt Summers lifted K5054 off the grass runway at Eastleigh Aerodrome on March 5, 1936, aviation history changed forever. The aircraft's performance exceeded every expectation. With its Rolls-Royce Merlin C engine producing just 990 horsepower, the prototype achieved 349 miles per hour, faster than any fighter in the world. But raw speed was only part of the story. The elliptical wing's true genius lay in how it managed airflow across its entire surface. Unlike conventional wings that created turbulence at the tips, the Spitfire's wing maintained smooth airflow from root to tip, generating lift more efficiently than any previous design. This efficiency translated directly into superior maneuverability. The aircraft could maintain energy in turns that would drain speed from other fighters. Mitchell had incorporated another critical feature: geometric washout. The wing was twisted so that the root had a positive angle of attack, while the tips were set at a slightly negative angle. This ensured that during a stall, the wing would lose lift at the root first, giving the pilot clear warning through buffeting in the control stick, while keeping the ailerons at the wingtips effective for recovery. The first production Spitfire Mark I rolled off the assembly line at Supermarine's Woolston facility in July 1938, nearly 2 years behind schedule. The delays weren't due to design problems, but to the unprecedented complexity of mass-producing such a sophisticated aircraft. Joe Smith, who had taken over as chief designer following Mitchell's death in June 1937, faced enormous challenges scaling up production. The elliptical wing required nearly 200 individual parts, each machined to tolerances measured in thousandths of an inch. The compound curves of the wing's upper and lower surfaces had to be formed by hand, using wooden templates and skilled metalworkers who could shape aluminum to within a fraction of a millimeter. Each wing contained 63 separate ribs, precisely spaced to maintain the wing's shape under extreme loads. The main spar, constructed from aluminum and steel, had to withstand forces of up to 12 times the aircraft's weight during combat maneuvers. The engineering challenges were so complex that Supermarine initially struggled to build 5 aircraft per week, far below the Air Ministry's urgent requirements. By September 1939, when Britain declared war on Germany, only 306 Spitfires had reached RAF squadrons. Number 19 Squadron at RAF Duxford received the first operational aircraft in August 1938, but pilots quickly discovered both the tremendous potential and dangerous limitations of their new fighter. The Spitfire's Merlin engine used a float-type carburetor that created a critical vulnerability in combat. When the aircraft experienced negative gravitational forces, such as during a sudden dive or inverted maneuver, fuel would float away from the carburetor intake, causing the engine to cut out completely. German pilots flying Messerschmitt Bf 109 fighters with fuel-injected engines could exploit this limitation by pushing into steep dives, knowing British pilots couldn't follow without losing power. The solution came from an unlikely source. Beatrice Tilly Schilling, a young engineer at the Royal Aircraft Establishment, developed a simple metal disc with a precisely calculated orifice that restricted fuel flow just enough to prevent flooding during negative G maneuvers. The RAE restrictor was retrofitted to all Spitfires by March 1941, though it didn't completely solve the problem. These technical challenges became brutally apparent during the evacuation of Dunkirk in May and June 1940. For the first time, Spitfires engaged German fighters over enemy territory, and the learning curve was steep and deadly. Squadron leader Robert Stanford Tuck, leading 92 Squadron Spitfires over the Dunkirk beaches, quickly discovered that the aircraft's superior turning ability came at a cost. In sustained dogfights, the thin elliptical wing generated enormous lift loads that could cause structural failure if pushed beyond its limits. Pilots learned to recognize the subtle buffeting that warned of approaching blackout conditions, usually around 4.5 G-forces, and to ease back on the controls before the wing's structure was compromised. But when flown within its limits, the Spitfire's wing design provided capabilities that astonished both friend and enemy. German pilots reported that the British fighter could outturn their Messerschmitts at almost any altitude, particularly above 20,000 feet, where the elliptical wing's efficiency became most pronounced. The Battle of Britain, fought from July through October 1940, became the ultimate test of Mitchell's wing design. Fighter Command adopted tactics that played to the Spitfire's strengths: high-altitude interceptions where the thin wing excelled, and turning engagements that exploited its superior maneuverability. At OR, Flight Lieutenant Jeffrey Quill, Supermarine's chief test pilot who also flew combat missions with 65 Squadron, later described the tactical doctrine that evolved. The Spitfires took on the 109s while the Hurricanes went for the bombers. It wasn't a hard rule, but it made sense. The Hurricane was more rugged, but the Spitfire could match the Messerschmitt in a turning fight. Jeffrey Wellham's combat experience with 92 Squadron illustrated both the aircraft's capabilities and its demands on pilots. At just 18 years old, the youngest pilot in the Battle of Britain, Wellham learned to manage the Spitfire's power through thousands of hours of aerial combat that compressed a lifetime of aviation experience into months. On a typical intercept mission over Kent, Wellham would climb his Mark I Spitfire to 25,000 feet, where the thin air played to his aircraft's advantages. The elliptical wing's efficient lift generation meant he could maintain altitude while maneuvering in ways that would cause other fighters to lose precious height. when German bomber formations appeared on radar, escorted by Bf-109 fighters. The engagement would begin at high altitude with diving attacks from out of the sun. Wellham learned to use his aircraft's superior turning radius to avoid head-on passes, instead forcing German pilots into turning duels where the Spitfire's wing design provided crucial advantages. In one particularly intense engagement over the Thames estuary, Wellham found himself pursuing a Heinkel HE-111 bomber that was diving toward cloud cover. As he lined up for a deflection shot, a Bf-109 dropped out of the sun behind him, its twin 20mm cannons seeking his aircraft. The German pilot's advantage in firepower was significant. His cannons fired explosive shells, while Wellham's 8 Browning machine guns used solid bullets that often passed through enemy aircraft without causing critical damage. But the Spitfire's elliptical wing provided the edge he needed. Wellham hauled back on the stick, feeling 4 G-forces press him into his seat as his aircraft pulled into a climbing turn that few other fighters could match. The Bf-109 pilot tried to follow, but couldn't maintain the angle of attack, his aircraft sliding sideways through the turn as its wings approached the stall. The German fighter's wings were designed for speed rather than maneuverability, with a straight taper that created uneven lift distribution. At high angles of attack, the wingtips stalled first, causing the aircraft to snap into a dangerous spin. Wellham had been taught to exploit this weakness, using his superior turning ability to force enemy pilots into positions where their aircraft's limitations became apparent. As the Messerschmitt fell away in a half-controlled stall, Wellham continued his climb, using the elliptical wing's efficiency to convert his airspeed into altitude that could be traded back for speed when needed. This energy management became crucial as fuel supplies dwindled, and return flights to base required careful conservation of both fuel and altitude. The Spitfire's internal fuel capacity of just 85 gallons provided only about 90 minutes of flight time, including combat. Pilots learned to monitor their fuel gauges carefully, knowing that running out of fuel over the English Channel meant almost certain death. The elliptical wing's efficiency helped extend range slightly, but the aircraft remained fundamentally limited by fuel capacity throughout the war. As the Battle of Britain progressed through the summer and autumn of 1940, Supermarine and Joe Smith's design team worked frantically to improve production rates and address the combat lessons flowing back from frontline squadrons. The bombing of the Woolston and Itchen factories in September 1940 forced a complete reorganization of production into dispersed shadow factories across southern England. This dispersal actually improved the aircraft's development pace. Smaller production centers could more easily incorporate modifications and improvements without disrupting entire assembly lines. By late 1940, Spitfires were rolling out with improved armor protection, 3-blade propellers that enhanced performance, and the first experiments with cannon armament. Isatin, the Mark V. Spitfire, introduced in early 1941, incorporated the first major evolution of the elliptical wing design. While maintaining the same planform, engineers strengthened the wing structure to handle higher loads and incorporated provisions for different armament configurations. The Universal C-wing could mount either 8 machine guns, 4 20mm cannons, or a combination of both. But even as production ramped up, new threats emerged. The introduction of the Focke-Wulf FW-190 in August 1941 caught the RAF completely off guard. The German radial engine fighter was faster than the Spitfire Mark V at low altitudes and could dive away from combat when the tactical situation turned unfavorable. Joe Smith's team responded with the Mark IX, powered by the new Merlin 61 engine with a 2-stage supercharger. This power plant increased output to 1,660 horsepower and included a Bendix-Stromberg injection carburetor that finally solved the negative G fuel cutout problem that had plagued earlier variants. The first Mark IX flew in April 1942 and immediately demonstrated performance that shocked test pilots. With a top speed of 408 miles per hour at 25,000 feet and a climb rate approaching 4,000 feet per minute, the new variant could match or exceed the performance of any German fighter. Jeffrey Quill's test report captured the significance. The performance of the Spitfire 9 is outstandingly better than the Spitfire 5, especially at heights above 20,000 feet. On the level, the Spitfire is considerably faster, and climb is exceptionally good. It will climb easily to 38,000 feet, and when leveled off, there can be made to climb in stages to above 40,000 feet. The elliptical wing's efficiency became even more pronounced at these extreme altitudes. In the thin air above 30,000 feet, conventional wings lost effectiveness rapidly, but the Spitfire's mathematically optimized planform continued generating sufficient lift for combat maneuvers. This high-altitude performance proved crucial as German tactics shifted toward high-level reconnaissance and bombing missions. Photo reconnaissance Spitfires, stripped of armament and equipped with cameras, exploited the wing's efficiency to achieve ranges exceeding 1,500 miles with additional fuel tanks. These unarmed aircraft relied entirely on speed and altitude for survival, often operating at 40,000 feet where the elliptical wing's advantages were most pronounced. The wing design faced its greatest challenge with the introduction of clipped wing variants in mid-1943. By removing the elliptical wing tips and replacing them with square-cut fairings, engineers increased roll rate and improved low-altitude performance at the cost of high-altitude efficiency. The modification was controversial among pilots and engineers. Beverly Shenstone opposed the change, arguing that it eliminated the aerodynamic benefits that made the Spitfire unique. But combat experience over occupied Europe, where missions increasingly involved low-level ground attack, demonstrated that improved roll rate and reduced wing loading were more valuable than theoretical aerodynamic perfection. Test flights revealed that clipped-wing Spitfires could roll 60 degrees per second compared to 45 degrees for standard aircraft. This improvement proved crucial in the fast, low-altitude combats that characterized the later war period. The modified wing also provided better acceleration below 10,000 feet, though it reduced maximum ceiling by approximately 3,000 feet. As the war progressed, the fundamental wing design remained constant even as the aircraft around it evolved dramatically. The Mark 14, introduced in late 1943, incorporated a massive Griffon 65 engine producing 2,050 horsepower, more than twice the output of the original Merlin. This enormous increase in power required extensive modifications to the aircraft's structure. The engine was mounted 10 inches further forward to maintain proper balance. The propeller grew to 5 blades to absorb the additional horsepower, and the vertical fin was enlarged to handle the increased torque effects. Through all these changes, the elliptical wing planform remained unchanged. Jeffrey Quill flew the first production Mark 14 in October 1943 and immediately recognized its significance. So the Mark 14 was in business, and a very fine fighter it was. It fully justified the faith of those who, from the early days in 1939, had been convinced that the Griffon engine would eventually see the Spitfire into a new lease of life. The Griffon engine rotated in the opposite direction from the Merlin, creating unfamiliar handling characteristics that caught many pilots off guard during takeoff. The powerful torque effects required careful rudder inputs to maintain directional control, particularly during the vulnerable moments immediately after leaving the ground. One experimental Mark 14 was fitted with a 6-bladed contra-rotating propeller that eliminated torque effects entirely. The aircraft flew beautifully, maintaining perfect directional control throughout its flight envelope. However, the complex gearbox required to drive the contra-rotating propellers proved unreliable in service conditions, and the system was abandoned for single-engine applications. By early 1944, Spitfire production had reached peak efficiency across multiple factory locations. Castle Bromwich alone was producing over 100 aircraft per month, while the dispersed shadow factories contributed hundreds more. The total production eventually reached 20,351 Spitfires across all variants, making it one of the most produced fighter aircraft in history. The war's end in May 1945 didn't mark the conclusion of Spitfire development. The final variants, the Mark 22 and Mark 24, incorporated extensive modifications including cut-down rear fuselages with bubble canopies, increased fuel capacity, and provisions for rocket projectiles and bombs. These late-production aircraft bore little resemblance to the original Mark I beyond their distinctive wing planform. They were twice as heavy, nearly twice as powerful, and capable of carrying external stores that would have been unthinkable in 1936. Yet the elliptical wing continued to provide the fundamental aerodynamic efficiency that made such performance possible. The Spitfire's naval variants, known as Seafires, presented unique challenges for the wing design. Carrier operations required structural modifications to handle the violent deceleration of arrestor hook landings and the corrosive effects of saltwater spray. Despite these challenges, the elliptical wing's strength and efficiency made successful naval adaptation possible. Late-model Seafires incorporated folding wings to reduce storage space aboard aircraft carriers. The wing fold mechanism had to maintain the structural integrity and aerodynamic properties of the original elliptical design while adding the complexity of hinges and locking mechanisms. The engineering challenge was enormous, but the fundamental wing shape remained unchanged. Production finally ended in February 1948 with the completion of the last Mark 24. In total, 24 major variants and dozens of sub-variants had been produced, each incorporating lessons learned from combat experience and technological advancement. Through every modification and improvement, the elliptical wing remained the aircraft's defining characteristic. The Spitfire's combat record speaks to the success of Mitchell's wing design. RAF and Commonwealth pilots achieved thousands of aerial victories flying aircraft built around the elliptical planform. The wing's efficiency allowed Spitfires to operate effectively from the scorching heat of the Mediterranean to the frozen airfields of northern Russia, adapting to conditions that would have grounded less capable designs. Survived the war to become one of the last living veterans of the Battle of Britain. His memoir, First Light, captured the intimate relationship between pilot and aircraft that the Spitfire's responsive handling made possible. He wrote of the sensation of pulling 4 G-forces in a tight turn, feeling the aircraft respond to the slightest control input, trusting in the engineering excellence that kept him alive through hundreds of combat missions. The elliptical wing that made such performance possible represented more than aerodynamic efficiency. It embodied a design philosophy that prioritized both performance and pilot survival. Combined with his pursuit of speed, created an aircraft that could be pushed to its limits without betraying the pilot who depended on it. In the end, the Spitfire's dangerous wing proved dangerous only to its enemies. The mathematical precision of its elliptical planform, optimized for minimum drag and maximum efficiency, provided the performance margins that kept Allied pilots alive through the most intense aerial combat in history. It was, quite literally, the wing that helped win the war,